Yes, my dear students, as you people said, we were discussing about the statistical characterization of the correlator outputs, right? So we have determined what is the mean variance, right, of the correlator output, and as well as we found that they are statistically independent, right? Right? I think we were there till that point. Okay. Uh, yes. Is it possible to say any one of you what is the value of mean and variance of the correlator output, which is a random variable, right? Xj, what we say, right? What is its mean and variance? Quickly, yes. What is the value of mean? I think majority have done this question. What I observed in the test. Let's be fast. Mean and variance. What is the mean of that random variable, and what is the variance of that random variable?
Mu xj is equal to Sij.
Yeah, mean is Sij, and variance is what? Yes, what is the value of variance we
N
got?
naught by 2.
N naught by 2, right? So which is equal to the power spectral density of the noise, right? Fine. So with that recap, so let me uh, continue further discussion about that. Okay. Starting. So similar to the signal vector, no, even we can represent the output of the correlator. Okay, the output of the n correlator as a vector. Okay, that is in simple words what I can say. It is just uh, it is just an vector which is denoted by x of n random variables. Okay, uh, so is it possible to write in that way? How I wrote? Minute. Sorry. No. 1 minute. So I'm finding some issue with Word file. So I'm opening this whiteboard. Yeah, it may take 1 or 2 minutes. So till that, I hope are we able to get the idea how we can represent the output of the correlator n correlator x as a vector? Is it possible to say it is a column vector, right? So I can say x is equal to x1, x2, and so on up to xn. Right? That is how we express the output of the n correlators as the vector. Fine. So as I said, the elements of the vector x are statistically independent. Then when they are statistically independent, so how do we determine the conditional probability density function? Hope you are aware of the probability density function. Hope you might have studied this even in linear algebra and as well as mathematics also. So we are likely to use maximum a posteriori rule, that is a map rule, okay, and even this Gaussian probability density function. So if not, I will tell there and then what is what. I think you should be able to catch that point. Okay. I think still it is not opened. That is a problem. Uh, Let me stop presenting. Yes, hope you are able to see the whiteboard now. Hello.
Yes,
Yes, sir.
Yeah. Uh, yeah. So as I said, the this is the output of the n correlators. It is a random variable, right? So this I can express as I said as a vector, right? So x is equal to as a column vector I can represent. So I can write as what x1, x2, and so on up to xn, up to xn. Okay. So let me call. I think is it possible to say anyone of you remember what is the equation number I've given? I am correct. I think is it 14?
Yes, sir.
Yeah. So what is this one? This is the uh, I am expressing output of the n correlator outputs as a vector, right, with n random variables. So now already we have proved that the elements of the vector x are statistically independent, right? So now what I was telling is the conditional probability density function. So let me write that the conditional the conditional probability density function I write in short, so as PDF. So you all should understand PDF means probability density function. Okay, the conditional probability density function, which I denote as what, fx, okay, of uh, small x conditional probability. I hope you are all able to understand this. What I write, fx of x slash mi, right, means uh, this of this is a conditional probability density function of mi sent and x received. Okay, where m suffix I is the message symbols. Okay, or what I can say for signal si of t sent, right, and x is the received symbol. Fine. Of the vector x, right, the conditional probability density function, which I denote as what, fx of x conditional mi, means mi symbols transmitted and x is the received signal, right, uh, of the vector x, given that what I said, the symbol, given that the symbol mi, or I can say uh, signal si of t, okay, signal si of t is transmitted. Si of t is transmitted. So I write transmitted as like this, tx1. Okay. So the conditional probability density function, what is that? Fx of x slash mi of the vector x, given that the symbol mi, or I said the signal si of t is transmitted, can be expressed as the product of the conditional probability density functions of its individual elements. Okay, so I repeat once again, the conditional probability density function fx of x slash mi of the vector x, given that the symbol mi or the signal si of t is transmitted, can be expressed as what, the product of the conditional probability density functions of its individual elements. So is it possible to say how do we express that? So I think instead of writing the sentence, I can write the equation. I should be able to understand. But let me write that. So I said the conditional probability density function can be expressed, right? Said can be expressed as, can be expressed as the product of, right, the product of the conditional product of the conditional probability density functions. So I write as PDFs, probability density functions of its individual elements, of its individual elements, of its individual elements. So is it possible to help me? How can we express this mathematically? So what I told in words should be expressed in terms of mathematics. Yes, anybody can help? I said the conditional probability density function fx of x slash mi of the vector x, given that the symbol mi, okay, is transmitted. can be expressed as what I said, the product of the conditional probability density functions of its individual elements. Yes, how can we write? How do we write the product symbol? Yes, my dear students, please help me to write that expression. Hello? Hello? Yes? Is it possible to say? Hello? Yes, nobody responds. Okay, say fx of, right, x slash mi is what? Is the conditional probability density function of the vector x given that the symbol mi is transmitted, right? Which is equal to what I said. It is the product of the conditional probability density functions of its individual elements. So the condition means product we write by this notation, right? Pi, where the value of that can vary from j is equal to 1 to n, right? Then we say individual, right? Product of the conditional probability density functions of its individual elements. Individual elements means fxj, right? Fxj of, so this xj is the individual element, right, for the transmitted symbol mi. So this is how we express. So let me call this as equation 15. Okay. Hope are you able to understand what I am saying? I said the conditional probability density function of the vector x given that the symbol mi is transmitted can be expressed as what? I said product of the conditional probability density functions of its individual elements. So that is why I write fx of x slash mi is equal to, by j is 1 to n, fxj of xj slash mi, right? So if the channel satisfies this equation, okay, then we say the channel is memoryless. Okay, a channel, okay, a channel that satisfies, a channel that satisfies equation 15 is said to be memoryless. What do you mean by memoryless? Yes, any idea? Memoryless channel. We say it is a memoryless channel. Yes, any idea about that memoryless channel? Means it depends on only the state of that output channel, depends only on the present input, right? Not on the past or future also. Okay, that is what we say the channel is memoryless. Okay. Fine. Here, I think let me just quote what is what. Though already it is told, this what is small x I write. This is what? This is the sample value of the random vector x. Sample value of the random vector x, capital X. Okay, this x what I wanted to say here, small x means, and as well as this xj, right? Xj is the what? Sample value of the random variable xj. I think I can just say like this, is the sample value of the random variable xj. Okay, and as I said, this is the what I say small x is the observation vector. We call this as an observation vector. Observation vector, and small xj is the what element of the observation vector. Element of the observation vector. Okay, so these are some key terms which we are going to use again and again. So already told many times, still I once again repeating what is what. Okay, so with this understanding, so let me say the Gaussian random variable, we all know how do we express that, right? So we can express the Gaussian random variable by its mean and variance, right? So with that, I can say the each random variable xj, okay, as I said, a Gaussian random variable, a Gaussian random variable is completely described by is completely described by its mean and variance, right? Its mean and variance. Okay, so with that I said that each random variable, what is that? Each random variable, that is xj, right, will be expressed with what? It's a mean of, what is its mean? Already you people said it is Sij, mean is Sij, and the variance, right? And variance is n naught by 2, and variance is n naught by 2. So this is the mean and this is the variance, right? So with that, so how do I express the probability density function? The probability density function, as I was telling, is I think, okay. So I hope you all aware of the expression, the Gaussian distribution function. Are you aware? So let me write the general expression. What is it? Gaussian distribution function, right? That is probability density function for the Gaussian variable. So just let me write in short, that is PD of probability density function. So which is equal to fx of x is equal to 1 divided by, okay, square root of 2 pi into the variance denoted by sigma x, right, into e power minus, right, I think, right, yeah, okay. So e power of what I can write, uh, so minus of this xj, right, minus mu, mu is the mean of this, divided by this square, divided by what, 2 into sigma square x. So this is the Gaussian probability density function, and we are assuming that xj is also a Gaussian random variable, right? So with that, so now let us try to substitute the value of mean and variance in this equation. So with that, what I can write, what can I write? The probability density function of the above equation, that is fxj, right, of xj This is a conditional probability density function, right? Mi. So which is equal to, so if I substitute variance as n naught by 2, or if I take it inside, it becomes sigma squared. So the 2 will get cancelled. So can I write it is square root of just pi n naught? Is this fine? If I take the sigma x inside, it becomes sigma squared x, right? The value of sigma squared x is what? N naught by 2. Fine. So if I substitute that here, 2 will get cancelled, only n naught will be remaining. So that is why I wrote 1 by root of pi n naught into e power, okay, e power. Then here also sigma squared x is equal to what? N naught by 2. So the 2 will get cancelled. I can write minus 1 by n naught, right, into xj, and we know what is the mean, that is Sij, right? Mean is Sij. Just substitute that. That's all. So this is the generalized expression for finding the probability density function. Just I wrote what is the probability density function for the random variable xj. Okay. So here the value of I can vary from 1 to m, and the value of j can vary from 1 to n. Okay. The value of I varies from 1 to m, and the value of j can vary from 1 to and so on up to n. So let me call this expression the number 16th. Okay.
So,
So now let me substitute. Yeah.
so equation 15, can you go here, sir?
Equation 15. Yeah. Yes, this is what the equation 15 is.
It's
So I
cap.
found this value. Okay, product of, yes,
So
I
it's
define what is it.
capital X, no, sir? F of capital X of X by mi.
Capital, yeah, f of capital X suffix j of small xj slash mi.
Small mi. And the one in bracket is also small, no, sir? In
Small?
the right hand side, sir. F of xj
Yeah,
open
f,
bracket.
yeah, f capital X of small x slash mi.
So right side, sir. Right
Yes,
hand
sir.
side.
Yeah, this side here.
In the bracket, sir.
Uh, yeah, in the bracket it is small x, no?
Yeah. Okay. Got it, sir.
Yeah, that small xj is the what sample of the sample value of the random variable capital Xj. Okay, so now let me
Got it.
substitute the value. I defined this function now, right? What is the PDF, probability density function of the random variable xj? So let me substitute that value in this equation 15. So by substituting that here, what can we simplify? Yes, is it possible to simplify and say what we can write? I said substitute equation 16 in 15. Yes, what can we write by substituting equation 16? Hope people have written this equation 16. Hello, is it fine if I move up?
Yes, sir.
Okay. So substituting 16 in 15, what is the simplified version I can write? Substituting substituting equation 16 into 15 into 15. So what I can write is fx of x slash mi is the conditional probability density function. So uh, so can I write this 1 by root of pi n naught as pi n naught to the power of 1 by 2 minus 1 by 2, right? And there the product, the value varies from 1 to n, right? So with respect to that, can I write the first term as pi n naught to the power of minus n by 2. Hope you are understanding this term. Why I write minus n by 2? Because I wrote that pi, right? The product term. There, the variable value j varies from 1 to n. So that is why I'm just writing pi n naught into to the power of minus n by 2. Right? Hope this point is clear. Then e power, right? The rest of the term e power, what I can write, minus 1 by n naught, right? Then summation j is 1 to n, j is 1 to n, then what xj minus sij square it is. Yes, hope you people are able to follow me what I'm saying. Just I substituted this equation in 15. I rewrote that in a simplified manner. Okay, so this equation, equation 17, okay, this will be this equation characterizes the first term of the equation 7. So what is that equation 7? Any one of you can say equation 7 I'm talking. What is that equation 7 is? Yes, be fast, at least should be able to support me. If you are having notes continuously, you will be able to tell that what is that. I said this equation completely characterizes, it completely characterizes equation 7. Yeah, may I know what is that equation 7? Equation 7 of the first term. Equation 7 of the first term.
So
Yes, quickly,
equation 7
anyone
was
of you can say what is that equation?
summation j equals to 1 to n xj phi j of t plus uh, w dash of t.
Yeah, yeah. So that is what? That is the received signal, right? What I just for understanding, I'm writing here. Okay, so x of t. Okay, just in bracket I write. Okay, so x of t will be equal to, just I repeat that what you said, that is summation j is 1 to n, right? Xj, then phi j of t, right, plus w of t. So this is what the equation 7 is, right?
That's all.
Yeah, this is what the equation 7 is. So in that, what is the first term I said? So let me keep this. So this is 7. Okay. In that, the first term is this one, right? So the above equation, that is equation 17, will be characterizing this term. What I wanted to say, it will completely characterize this term. Means this is what summation j is 1 to n xj pi j of t is nothing but output of the collator, right? So it will be completely characterizing that. So what I wanted to say here is, by using equation 17, it is possible to make the decisions, right, regarding which symbol is transmitted. So by using this equation, so hope you're able to understand what I'm saying. By using this equation 17, it is possible to take a decision, okay, or make a decision what symbol is transmitted, okay, which symbol mi is transmitted, right? Fine. Is that fine? What I'm saying is, are you agreeing? I said using equation 17, using equation 17, it is possible to make, it is possible to make a decision it is possible to make a decision regarding what I said, which symbol, regarding which symbol, what is that symbol is denoted by mi, right, is transmitted, which symbol is transmitted. Okay. So as I said, m suffix I, where the value of I can vary from 1 to m, right? So for making decision, only what we need a set of random variables xj, right, at the correlator output. That is what the meaning of this, right? Yes, what I wanted to say is, for making decision regarding what symbol is transmitted, what we need only the set of random variables, only the set of random variables. Just I write RV random variables, that is x suffix j, right, is required at the output of the correlator, at the output of correlators, right? So set of random variables xj is required. Let me write, is required at the output of the correlator. Hence, what we call this condition is known as the sufficient condition. Okay, so this we call it as what? Sufficient condition. Means if I know the random variable, I will be able to take a decision in favor of what symbol is transmitted from the transmitter side. Okay, so this is all little bit uh, probability theories involved. I think people should be able to visualize, because when we transmit symbols at the transmitter side, so at the receiver side, it all depends on probability. I need to use the probability theory only. There is no other way to determine what symbol is transmitted and how do I decide about that. That is why we are all discussing about this. Okay, fine. So with this basic understanding about that, so what is needed and what we call it as a sufficient statistics. Okay, sufficient statistics means what I told about that equation, right? So now just let me say about likelihood function. Are you aware of that likelihood function? Have you heard anywhere? What is that likelihood function? Yes, my dear students, should talk. Likelihood function.
No, sir.
So not heard only. Okay. You may be aware, but you may not be using the term. Oh, this is what is known as likelihood function. Okay. So whatever I have written, that conditional probability density functions, right, are known as the likelihood functions. Okay. The conditional probability density functions, the conditional probability density functions. Okay. What is the conditional probability density function I've written? F x of, right, x is small I, right, m suffix I. Okay, so where the value of I can vary from 1 to m are called the likelihood functions. Okay, the conditional probability density functions are known as likelihood functions. That I can write as a, then I can Okay. L is equal to, I can write fx of s slash m. Okay. So the likelihood functions are what? The conditional probability density functions of x slash mi are known as likelihood functions. I denote it as what? L of mi is equal to x of x slash mi. Okay. So let me call and here the value of I. Yes, hope able to see. Hello.
Yes, sir.
Yes, sir.
Yeah, thank you. So I was disconnected. At least somebody is in. Thank you, Kuber. You informed me. Otherwise, I will not be knowing whether I'm in. Okay. So what I was telling is the log likelihood.
So can you scroll on top, sir? We haven't
Yeah.
copied that.
Yes. I will write. So what I said is the likelihood functions. Yeah, I think this is fine enough.
Yes, sir.
Yeah. Yeah. What I said, what is likelihood function? I defined, right? The conditional probability density functions are known as the likelihood functions. I denote mathematically as what? L of mi is equal to fx of x slash mi. So usually we express these likelihood functions as log likelihood functions. So which is denoted as capital L of mi. So which is equal to ln, right? That is ln of L of mi. So I said I've already defined what is L of mi. That is conditional probability density function. So that is the equation 17, right? If I substitute that in this equation, I can say what is the log likelihood function for an additive wide Gaussian noise channel. So if I scroll up, is it fine? Yes, if I scroll up, is it fine? I'm asking.
Yes, sir.
So as I was telling, the log likelihood function, the log likelihood function for an additive white Gaussian noise channel, or an AWGN channel, is what I can write, uh, L of mi, which is equal to uh, okay, hope you are able to see that equation 17, right? If I substitute that here by taking logarithm, so I write by eliminating some term, I will say why I am eliminating that term. What is this? So I just write 1 by n naught into summation j is 1 to n, j is 1 to n, then xj minus sij square. Okay, so let me call this as equation 20. This is what I call as log likelihood function of for an additive white Gaussian noise channel. Okay, you all may wonder something is missing in this, right? So what I left is the constant term. What is that constant term? That is minus n by 2. Okay, minus n by 2 ln of pi n naught. Right? If I take log of that, first term, I will be getting this, right? So I am ignoring this term because it is a constant. It is nothing to do with the message symbol mi. Okay, so that is why I am ignoring this. Okay, is ignored. So hope why I said it is ignored. It is a constant term. The constant term, that is minus of n by 2 ln of pi n naught, right, is ignored because it is not related to the message symbol mi. Okay, because it is, or what I can say, it bears no relation. Okay, it is not related, or it bears no relation. It is not related to the message symbol mi. Message symbol mi. So that is why I am ignoring the constant term and writing the remaining terms. Hope this point is clear. Why I ignore this term? By taking log of that equation 17, this will be there. So I'm ignoring that and I'm writing the remaining term. That is minus 1 by n naught. Summation j is 1 to n of xj minus sij whole square. Okay. So here sij are the what? Elements of the signal vector si, that representing the message symbol mi. Right? Sij, what I said, are the elements of the signal vector si. Right? So let me write that to just get a clarity. Sij are what? Sij are the elements. Sij are the elements of the signal vector si. Yes or no? Sij are the elements of the signal vector si, that will represent this si signal vector will be representing what? The message symbol mi. Right? Si representing the message symbol message symbol mi. Okay, so hope so let me, I think, stop with this, right? So let me continue further discussion. That is the important one, and which is widely used. And what is the topic is optimum receivers using coherent detection. Okay, and it is a very basic and important also. So, and it is more of twisted also. Okay, I don't know how many of you will be able to grasp that, but let me try to make you understand an important thing. Okay, so is that fine? So next topic, what I'm going to discuss is about the what? Optimum receivers using coherent detection. So 1 minute, let me take the attendance online only.